Alright, good everyone. By request, I think I was going to do it anyway, but level 2 organic. This is 2014, so it's quite a while ago. So I wanted to start with some old papers because a lot of people do the recent ones as practice, but not so much the old ones. They're just as good. Right, let's get into it. Okay, so in the boxes below, draw a primary, secondary, and tertiary alcohol for this molecule. So remember, primary alcohols are when the OH group just connects to a carbon like on the end. So it'll look something on the lines of C C C C C C O H, and then you've got all your hydrogens like this. And you should be able to convince yourself that there are 11 hydrogens here, an OH group, and the 5 carbons. A secondary alcohol occurs when a secondary alcohol will occur if the OH group is joined to a carbon which is joined to 2 other carbons, like this. And again, you put all your H's on these guys. I won't bother drawing it in just to save time, just because I waste of time. Put all the H's around it. And tertiary occurs when your OH is joined to a carbon which is joined to 3 other carbons. So can be a little bit hard to visualize, but you know it's going to look something like this, and then you just add one more, and again, add H's onto the end of all those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There you go. So it's primary, secondary, and tertiary alcohols covered there. Pretty standard question. When primary alcohols oxidize by acidified permanganate, they form carboxylic acid. Kind of them to tell you that, I mean, they usually just expect you to remember that. Draw the primary alcohol that was oxidized to form the carboxylic acid. Funnily enough, it is the one I drew up here. That is just coincidence. But the idea here is the only thing that the permanganate does is it changes the sort of end, changes the OH, but it doesn't change the rest of the molecule. So the rest of the molecule, happy as Larry, you draw it all in. Then this last C, where the OH to thingy is here, you just put the OH group. So when this guy gets oxidized by permanganate, it takes this N carbon and transforms it into this guy here. So this becomes this. That's what happens under oxidation. Permanganate ion can be used to oxidize alkenes. Yep. Remember, an alkene is a guy like this with a double bond. So when you oxidize an alkene, you actually produce a type of alcohol, which we call a diol. We call it a diol because it produces two OH groups. So putting in all this guy. Now this here, I'm going to break the double bond. My hydrogens, I had 2 hydrogens on that N carbon, and 1 on that carbon there. And then these 2 links here that you've got open because you've got rid of the double bond become OH groups. And the reason we call it a diol is no surprises really, right? It's two hydroxyl groups in the end there. Okay, the reactions below are all classified as being the same type of reaction. I wonder if I can just testing with size. That's fine. Are all classified in the same type of reaction. So we got hexane reacts with bromine water. Hexphonyl reacts with ECl3, 1-chloro. Hexane reacts with concentrated ammonia. So, describe the type of reaction occurring, state whether any conditions are required. Okay. So, in all 3 cases here, this reaction is known as a keyword's broken, substitution reaction. Because one atom or group is being swapped with another atom or group. So, in all three cases, if you think about it, right, this reacts with bromine water, 2 hydrogens will go and be replaced with Br2, for a dibromo alkane. If this guy reacts with PCl3, the alcohol group is swapped with a chlorine group. And when this guy reacts with ammonia, the chlorine group is swapped with a NH2 group. HCl is driven off. So they're all substitution reactions. So let's go through and do this one by one. So reaction 1, we get a bromine. Oh, not dibromo. I got that wrong before. Yeah, whoops. A bromine swaps out a H. So yeah, that's the idea. So bromine comes along from the bromine water, it swaps out one of the H's, and that forms a bromoalkane and also hydrogen bromide. H and B1Br left. This thing requires UV light. That is a requirement. If you've done level 3 physics for whatever reason, you might actually know why that is. It's to do with electron energy levels, and bromine need to be excited by UV light. You don't need to mention that. But in reaction 2, a Cl atom replaces an OH group. Yep. So we had Cl coming in and swapping out with OH. And when that happens, there's not really any conditions required for this guy. It just sort of does it. If you give it a PCl3 or thionyl chloride, so SOCl2 works too. Even PCl5. Alcohols are quite they're quite happy to react and form stuff. So yeah, it'll form a chloroalkane or whatever, chlorohexane. Yeah, forms this guy here, chlorohexane. 3. So the Cl atom swapped by an NH2 group. No, it's not NH3 group, it's NH2 group. One of the H's on here joins with the chlorine and forms HCl, and that's driven off. And again, we don't really need conditions for this, except no, alcoholic. It needs to be alcoholic. NH3 for some reason, I'm not exactly sure why. Okay, so now we need to explain why 2 layers were formed. Explain why 2 layers were formed in reaction 1. So hexane is this big molecule, right? It's this really long thing. It's non-polar, and bromine water is also non-polar, but it's very small. And the bromine ions that can not bromine ions. I mean, like when this reacts, the hydrogen bromide creates bromine ions in the water. So the way you can put this is the hexane is non-polar, and effectively so is the bromohexane that's created. Bromohexane, because if you look at bromohexane, it's pretty big and it's not that polar. Large chain. It's got a really large chain, and sure it has a bromine on the end, but pretty large chain. The water, very good, but by contrast, bromine water is polar. It's not the easiest thing to see, but if you think about it, aqueous bromine water. Yes, these guys here by themselves are non-polar. However, when they react with hexane, you're going to get a hydrogen bromide forming, and that's going to dissociate and create bromine ions. And hydrogen bromide is, obviously quite polar. Things dissolve, right? Bromine water dissolves. Bromine dissolves in water, I should say. So bromine dissolves in water. That's the point. It's aqueous. The two layers don't mix together. Now the reasoning why that is because the okay, how do I put this? Yeah, I mean, typically the answer is just the layers don't mix together because there is a polar and non-polar substance present. Now the reasoning for that is if you have, it's not because they repel each other, it's just because the polar stuff is so much more attracted to itself. So consider the simple case of oil versus water, right? This is the classic example. Here's some water, here's some oil. And you ask, well, why are they separating? Now, you might think, oh, the water is repelling the oil, but it's not really true. What's really going on is the water is so much more attracted to itself. The water just likes itself better. So, if you put some oil in the middle here like this, all the water would squeeze it and say, no, I'm much more attracted to myself, and squeeze and squeeze and squeeze it, and just force it out, and it would pop up back up there. So that's the general idea behind that one. So if you have two layers which are polar and non-polar, it's not mixed together. Because the polar thing will squeeze out the non-polar thing. Yeah. Bromine something water. Well, yeah, bromine water is polar because water is polar, right? Bromine dissolves in the water. Yippee. Yeah. Awesome. Okay, let's move on. Complete the following table to show the structural formula and systematic name. What kind? Okay, butte 1 ion. An ion will only have, will have a triple bond. So it should look something like that. Remember, butte is code for 4 carbons, and 1 means the triple bond must be connected to the first carbon. So it's the 2,2-dichloropentane monol. So you hear pent, right? So there must be sort of 5 carbons involved. A 1-ol means there'll be an OH group there, and then if we count 2, 1, 2 to this one, dichloro, there must be 2 chlorines on the second carbon. This is the first carbon, this is the second carbon. Okay. This guy here is pentanone. There are a few different ways you could name this. Some other ones I think are pentylamine or 1-aminopentane, but all of them are correct. This next one is a carboxylic acid, and this methyl group is on the third thing. So it's 3-methyl, and then 1, 2, 3, 4, 5, 6. So hexanoic acid. So hex tells you there's 6 carbons in the chain. 3-methyl tells you that on the chain there's a break at the third carbon to get on the methyl group. And then acid because it's acid. And this guy here is 2, 4 dichloro, 2 chlorines on the second and the fourth, and then it's 1, 2, 3, there's 6 carbons in the chain, and a double bond in the third, so hex 3-ene. So hex 3-ene tells you it's a hexene, 3 tells you that's the double bond is 2,4-toluene. 4 as well. Right. Explain why compound A consists of geometric cis transisomers compound B and C cannot. Being your answer, you should draw the cis and trans isomers in compound A, explain the requirements, referring to comments A, B, and C. Okay, so cis and trans isomers occur because a double bond doesn't rotate very freely in space. It's just stuck. So there's two different ways you can arrange a molecule. Cis the cis isomer will be when everything not everything. Two similar groups are on the same side. So these two H's here are coming from this H and this H, connected to the two bonded carbons. But the other connection to this carbon here is the rest of the methyl chains, that guy there. And then on this carbon here is an ethyl group. There's a CH3, CH2. Well, we often segregate that to C2H5. So an ethyl group down here. So this guy here is representing all of this. Now, this is called cis because the two common groups, the H's, are on the same side. Whereas the trans isomer will be like this. And so what's going on there? Well, it's just rotated such that the H's are opposite one another. Because in space, this is two very different arrangements. You can't spin this carbon around to put this H here and this guy here. It won't turn because it's stuck in a double bond. Conversely, if you just had something which is like CCHLAB, all of these guys can spin and rotate and do whatever they want. So there's no two distinct structures. Right. Okay. So the requirements for cis-trans isomers. A double bond must be present. So all three compounds except for R, A and B satisfy this, C does not. Since a double bond is rigid and cannot rotate in space. So you can't rotate about the double bond. It's impossible. So yeah, cannot rotate in space. This means two different arrangements of molecules can be present around a double bond. Call those cis and trans as above. In compound B though, in compound B, one of the carbons in the double bond is bonded to two hydrogens, which look identical, and so cannot be distinguished, i.e. the cis and trans isomer look identical. So if you imagine looking at this thing here, imagine I just made this an H. And then I made this an H. Now you could argue to me, oh well hang on, it is different still, right? This guy and this guy are flipped. But you could actually just rotate the entire molecule, like 180 degrees into the page. And this would come down here, and this would go up here, and this would go up here, and this would come down here. Nothing would change on the right, and this thing would just look like this. So they're actually just, these two guys here are just 180 degree reflections of one another. Conversely, this and this and this are not just flips of one another. If you've rotated this by 180 degrees into the page, this would go down here, this would go up here, but these guys would switch as well, and that wouldn't line up with this side. So these two are distinct. So hence you can conclude, that B does not form cis-trans isomers. A meets both requirements, and hence the result. So compound A meets both the requirements, right? It has a double bond, rigid double bond, and it also has both carbons in the double bond being bonded to two distinct groups, so you can actually tell them apart. Awesome. Okay. Awesome. Right, so here we go. Sodium carbonate, hydrochloric acid, and sulfuric acid are each added to separate samples of three organic compounds. The structures of the compounds and the product of any reactions are given in the table below. Right, okay. Compare and contrast the reactions that do occur with different compounds from the above. Okay. Let's work out what happens when we do this guy here. This is an acid, this is a base. So it's an acid-base reaction. The acid will, I'm just going to write it in here for simplicity. The acid loses its proton, its H goes away, and it gains a sodium. So it's become a salt. And in part 2, we've got a base reacting with an acid, just the other way around now, right? A similar thing happens, you get the carbon chain 2, and then the base accepts one more proton and becomes NH2+. Describe the different type of reactions occurring and give reasons why they are classified as that type. So propanolic acid reacting with sodium carbonate. And sodium carbonate is an acid-base reaction producing the salt, water, and carbon dioxide. And then the salt is drawn above. As acid-base, because, well, it's a proton donate / accept reaction. So whenever that happens, whenever something just gives away a proton and something else accepts it, water, is it proton or something? Yeah, that's pretty much the idea. What's the proton? When you get propionamine reacting with HCl or H2SO4, then propionamine reacts with HCl or H2SO4. Same thing occurs. It's an acid-base reaction. Basic amine accepts one proton in each case. That's the idea there. So HCl and H2SO4 are both donating one proton. What do we got here? When propanol reacts with HCl, a substitution reaction takes place. So when propanol reacts with HCl, a substitution reaction takes place. So what's going on there? Well, this OH group is being swapped with the Cl group, essentially. So HCl is coming in, it's putting a Cl on there, and we're taking the OH off, and water's formed. So HCl comes in, the H joins with the OH to make water, and the Cl just pops in the end. Yeah. This creates water and swaps the OH with the Cl group. And it forms forming a chloroalkyl. When you get this guy here reacting with identifying specific reaction, specific conditions that are required. That shouldn't require conditions, that shouldn't require conditions, shouldn't require conditions. However, going from an alcohol with H2SO4 to a alkene like this is elimination. So an entire OH group is being eliminated and a hydrogen as well. So this carbon remains unchanged, this carbon loses a hydrogen, this carbon loses an OH group. So water is being driven off. In the last case, concentrated H2SO4 is required. Water is driven away in a elimination reaction, removing the OH and H atom and creating a double bond, which is an alkene. So let's sum it up again. We got this guy reacts with this guy under heat and concentrated thing. That's the specific conditions. OH goes away. One hydrogen off this guy goes away. That H and the OH combine to form water, and that's what's driven away. And the double bond forms. That's the idea there. Yeah, that's that. Oh, there goes. Yeah, again, you should probably write a little bit more than this. Well, I mean, I've covered everything, but they do have to get a bit picky with your answers. Make sure you say everything. Okay, reaction scheme. Explain why reaction 1 is an addition reaction. So, an addition, it's addition because a double bond breaks and the H and Cl are added in the gap. So double bond breaks, one hydrogen, one chlorine is put on, double bond breaks, other way around, right? Chlorine's put on this one, hydrogen's put on this one. Yeah, so added in the gap, that's the idea. The major product is such that the carbon which has the most hydrogens to begin with gains another. So out of these two carbons, this guy had the most to begin with, he had 2, this one only had 1. So the major product will be such that the one with 2 becomes 3, and the one with 1 just keeps 1. The minor product is the one where the one with 2 keeps it at 2, and the one which had 1 gains the extra 1. The external reaction to the reaction scheme above showing it was classified as an elimination reaction. An elimination reaction occurs because a double bond is forming, and if we look at this very carefully, a Cl has disappeared, and also and a Cl and H have been eliminated, and they just disappear as hydrochloric acid. So this Cl is gone, so it's out the window, and this guy here as well. One of the hydrogens disappeared, and he's gone. So the HCl is driven away, but like how water was driven away with the alcohol going to the alkene. Elimination reaction occurs with double bond is forming, and then Cl and H have been eliminated, disappearing HCl. So there you go. Reaction 4 is also elimination reaction. Asking for draw the structural formula. Okay, let's put it. Reaction 4. Okay, so let's draw it up here as well. We got potassium hydroxide, alcoholic, sitting on this guy here. Now, when you add, I shouldn't say add, already, but potassium hydroxide, alcoholic, to a alkane with an alkane with a special group on it. It eliminates it back to an alkene. Now the way to remember this is if you go from an alkane to an alkene, you need potassium hydroxide alcoholic. If you want to go from a haloalkane to an alcohol, you need a hydroxide but non-alcoholic. So it's reverse psychology, essentially. You get an alcoholic potassium hydroxide, you're going to create a alkene from your haloalkane. If you get a non-alcoholic one, just an aqueous one, you will create another. It's counterintuitive. And what goes on here? Well, everything's pretty much unaffected until right at the end it's an OH group instead of OH group instead of the Cl group. It's extremely exciting. So yeah, there it is. So CH2, CH3 looks. Oh wait, I'm selling it now. Oops. That's sorry. That's creating the alcohol. I got myself confused. When it's alcoholic, you create an alkene. Yes. The double bond should be forming here. Yeah. Yeah, that's it. Yeah. Sorry. Pretty strange. There we go. Draw 2 repeating units of the polymer formed in reaction 5. Okay, so reaction 5 creates a polymer, which is interesting. This guy here, all the double bonds essentially break and they're linked together. So what you should do is start by drawing the 2 carbons in the double bond. This guy here is C3H7. This is just the same as this drawing here, except there's no double bond anymore, right? The exact same as this drawing here. And what you do is you line up you line them all up side by side, like that. And then when the double bonds broke, think of it as like levering out, and they link up together. So, and then we go onwards like that. And it goes on forever. Well, not forever, but it goes on for a very long time. Same idea is going on here. If you think about this guy here, right? You can convince yourself that this is the exact same idea. Hopefully. Yeah, go on above. Go look above. Compare and contrast the polymer formed in reaction 5 to reaction 3. Right. Let's have a look. Okay, so what's similar and different about these guys? Well, they actually have the same amount of hydrogens per each repeating unit, like the line through here. There is indeed 10 hydrogens here and 3 carbons. So they're actually structural isomers of one another. They are distinct, right? These two are not the exact same. They are very different. But this methyl here and this ethyl here could be added in a sense to make propyl group down here. Not physically, but numerically. So it's 4 carbons, 4 carbons, no, 5 carbons, 5 carbons, 5 carbons in each. These are 3, 4, 5, and 10 hydrogens. They're actually structural isomers of one another. So you could put this, I guess, as the molecular formula would be the same, but they are arranged differently in space. So are structural isomers. Okay, so why did this happen? Why these polymers from these two reactions are different? So you break this down and say, well, addition polymerization occurs when lots of alkenes break their double bond and all link together. Right. Hence, the position of the double bond pretty much dictates what the polymer looks like. Now, why are these guys different? Well, let's have a look. This guy here has a carbon, the double bond on the end. This one has it in the middle-ish. So, one on the end will definitely have a double hydrogen unit, whereas the one over here can't have a double hydrogen unit. It will always have a methyl group sitting off to the top at each of these guys, like it's in the middle. Since one has a double bond on the end and the other in the middle, the repeating unit is fundamentally different. Fundamentally different from that same reason I just outlined before. So, this guy here, each repeating unit will just have the 2 H's going up and down each time. But this guy over here can't do that. It's going to have an H and a CH3. They're fundamentally different. And there you go. One's double on the end, and the other in the middle. The repeating unit is fundamentally different. So you could outline why that is. Like, one has 2 hydrogens attached, so it has a CHH repeated unit while the other does not have this. And that pretty much does it for that one. Again, I would explicitly say a few things a bit more. Like you could physically say double bond is in position 1 or on carbon 2 or whatever, and just be a little bit more explicit. But that's all the concepts you need there. But in your answer, though, you will get points for saying words like in reaction 5 or this reagent or in this carbon position, which I have been slightly slack on, but the goal of these is to get the concepts to how you write your answers and something you've got to practice yourself, because that's just the way it is. Anyway, that's that one. Have a good one. Any questions, leave in the comments.